So what I'm going to show you in this video is how to get Bayesian estimates of your fit parameters and their uncertainties using pytc. And so what I've done already is I've loaded in an experiment just like we did previously, and now we're going to sample possible solutions to this fit in a Bayesian fashion. And so to do this, go up to fit options as opposed to fit options there. And you can select different types of fit. Maximum likelihood is the default. That's just find the best estimate of the parameters. We could also do bootstrap fitting, which samples from the uncertainty in each heat and then does maximum likelihood fits to each of those pseudo-replicates. But what we're going to do right now is a Bayesian sampling. And what a Bayesian sampling is going to do, it's going to use markov-chain Monte Carlo methods to basically walk out and explore the parameter space, the likelihood function, to build a distribution of possible solutions to, or possible model coefficients that fit these data. And so there are a variety of parameters that you can use to control this. We'll just walk through them one by one. The burn-in is when it starts the sampling, it's going to ignore the first, in this case, 10% of the data that goes into the fit. The initial Walker spread is we're going to start out with some guess for our parameters. This is how much noise to add to each of those parameters to create a collection of different walkers that are then going to walk out and explore the likelihood surface. We have what our initial guess is going to be. Is it going to take our fit parameters, or in this case, our parameter guesses as the starting point, or is it going to use our maximum likelihood guess as the starting point? In this case, we're going to use the ML guess. The number of steps is the number of steps that are going to be taken by each walker. And then the number of walkers is how many different walkers are going to spread across the surface. So if you have 100 walkers taking 100 steps each, that's 10,000 samples from the likelihood surface. And then we're going to say we're going to throw out the first 10% of that for burn-in. So we're going to get 9,000 samples of the likelihood surface for this analysis. Okay, so we have our parameters, our control parameters set there. Now we can do our fit just like we did for the maximum likelihood fit. And took a little bit longer than the maximum likelihood fit, but it was still extremely fast. What you'll notice here now is instead of having a single model fitting our data, we now have a whole collection of different fits shown by the sort of spread and cloudiness. And you can see that in our residuals as well. The residuals are now a collection of sort of fuzzy residuals corresponding to many, many different models that are describing the data. Just like the maximum likelihood fit, this will spit out a variety of fit statistics in the top. Notably, it'll spit out these things with a Bayesian in front of them that just tell you the parameters you used when doing the fit. And as before, we get estimates of all of our fits as well as uncertainties. In this case, it's going to spit out the mean of the Bayesian posterior distribution, posterior probability distribution, and then the 95% confidence intervals are actually estimated by numerically integrating that distribution. Now, one of the things about a Bayesian fit is your sampling, so you want to make sure that you've sampled enough. So if you were to do this in practice, I highly recommend extending out your number of steps and basically making sure that you are converging on a solution as you do the analysis. Another really useful tool when thinking about a Bayesian fit are these corner plots here. What these corner plots let you do is actually, what they're actually showing now is the sampling of the different parameters in the fit. So this is the sampling of our binding constant, the sampling of our enthalpies. And we look at that and we say, man, that is kind of a weird looking distribution. That's kind of a weird looking distribution. And the covariation matrix, or the covariation plot, looks a little bit funky. What's that saying is we've undersampled our fit. And so we can just go and make that longer. So now instead of doing 100 steps, I'm going to do 300 steps. So it'll take 3 times as long, but hopefully we'll get better convergence on this fit. So I'm going to start that running. And what I'll do, I'll just say the underlying package that we're using for the markov-chain Monte Carlo is a great package called MC. Highly recommend it. It's a very fantastic Bayesian package for Python. Okay, so here we've done our fit, ran a little bit longer, but still not very long at all. And now what we see is we're getting a much better sample of these distributions, and something interesting is appearing. We're actually starting to see more covariance in the estimates of these parameters, where, like we saw with the maximum likelihood fit, actually, as you increase your binding constant, you see a decrease in your binding enthalpy. So you can imagine iterating this, doing more samples even to make sure that you reach a solution that you're confident is stable. Okay, so that is how you do. And then also this can be exported in the same way that you can export a maximum likelihood fit.